Section 2.3 deals with continuity. So we say this: a function is continuous at some point if at that point it does not have any holes, any jumps, breaks, or gaps. So what I typically tell students is think about, can you draw this thing without having to pick up your pencil? If so, then you're going to be able to say that you are continuous. Now, usually you encounter holes, jumps, breaks with rational functions, even root functions, and piecewise defined functions. So these three types of functions are the ones that are going to typically, not always, but typically give us things that have a hole, a jump, or a break. How do we show that a function is actually continuous? What is the actual definition and what we're going to need to show and understand in this course? We can't say, I could draw it without picking up my pencil. Well, three things need to be met. Three conditions need to be met in order for you to be continuous at some point. The three conditions are as follows. The first one, f of c has to be defined. Condition number 2, the limit as x approaches c of f of x exists. So you have to have a limit. You can't write does not exist. It can't be positive or negative infinity. It has to exist. And finally, the third condition, the limit has to equal the function value. So these three things have to be met in order for you to be continuous at a point. You have to be defined at that point, you have to have the limit exist at that point, and the limit must equal the function value. So we say that a function is continuous over some open interval if it's continuous for every point within that interval. So you're continuous at a point if you can prove all three of those things are met, but we say that a function is continuous over some interval as long as it's continuous for every point over that interval. So let's use the graph to answer the following questions. The first question is find the function value. Find f of 2. Well, we know how to do that. We go to 2. We have a closed circle at 2, so f of 2 is equal to 2. Well, what's the limit as x approaches 2 from the right? That's the next thing. Well, that's numbers to the right of 2. So as we come in, looks like we're heading to 3. What about the limit as x approaches 2 from the left? Well, we come in and we get closer to 3 as well. So what's the limit as x approaches 2 of this function? Well, the limit from the left and the limit from the right are going to 3. So we can notice here that the limit as x approaches 2 of our function is also going to 3. So is this function continuous at x equal 2? Explain. All right, so three things need to happen in order for you to be continuous at a point. First, f of c needs to be defined. Is f of c defined? Yep, there's a closed circle there, so we're good. F of c defines. Part 1 is done. 2, the limit has to exist. Did the limit exist? It sure did. The limit as x approaches 2 of f of x is 3. Great. Condition number 3, the limit had to equal the function value. So does the limit as x approach 2 of my function equal f of 2? Well, does the number 3 equal 2? No, it doesn't, right? The limit does not equal the function value. So is this function continuous? No. And the reason why is because the limit as x approaches 2 of f of x does not equal f of 2. The limit doesn't equal the function value. Now, you'll see a question in my math lab like this. It's going to say, okay, well, what value should be assigned to in order for this to be continuous? So basically what it's saying is that in order for this to be continuous, instead of having f of 2 be 2, what should f of 2 actually be? Well, f of 2 should actually be 3. So if you see that on my math lab, what they're trying to look for is, okay, what should this actually be? Well, it should really be 3 in order for you to be continuous. But this function is not continuous. Why is it not continuous? Because the limit as x approaches 2 of x doesn't equal f of 2. Again, remember I told you guys that one of the ways to look at it is you can draw this without having to pick up your pencil. Well, if you look at this function, there's no way you could draw this without having to pick up your pencil. At one point, you have to pick up your pencil to fill in this dot. So if you have to pick up your pencil, you are not continuous. But you have to tell me why you're not continuous. All right, let's look at number 2. Same thing. 1. First, find the function value. What's the function value? Well, f of 1 is 0 because a closed circle is at 0. Now, what's the limit as x approaches 1 from the right? Well, coming in from the right, it looks like I'm going to the number 2. What's the limit as x approaches 1 from the left? Coming in from the left, I'm going to a y value of 0. Well, what's the limit as x approaches 1 of this function? Well, what happens when you're not going towards the same number? What happens with from the left I'm going to 0, from the right I'm going to 2? Well, we say then that our limit does not exist. So is the function continuous at x equal 1? Explain. The answer is no. Why is it not continuous? Because the limit as x approaches 1 of f of x does not exist. Because the limit as x approaches 1 of f of x does not exist. So again, in the My Math Lab question, it's going to say, can you assign a value here for this to work? And here you can't assign a value. Why? Because if the limit doesn't exist, assigning the value of this one to be 2 or anything like that, it's just not going to make this any better. Continuity. So let's look at continuity of some functions. So what we're going to be asked to do is determine if a function is continuous. And instead of giving a picture like we were in examples 1 and 2, we're going to be given the function. So let's just talk about continuity of some functions. So the first function we want to look at is the constant function. So the constant function is f of x equals k, where k is a constant. Well, that is continuous for all x. That's just a horizontal line. Horizontal lines are continuous everywhere. The second type of functions that we're going to look at are polynomial functions, and those are the x to the n, so x raised to a power, or n is a positive integer. Well, those are also continuous for all x. So polynomial functions are continuous everywhere, constant functions are continuous everywhere. So let's just answer number 3 real quick and then go on to the next ones. So we want to use theorem 1, here's theorem 1, to determine where each one of the functions is continuous. Well, what is f of x equals x cubed minus 2x squared plus x minus 1? Well, this guy here just happens to be a polynomial function. How do I know that? Because it's x raised to positive integers. X cubed, x squared, x to the first power. So, since that's a polynomial function, we can say that this is continuous everywhere. Or we could say negative infinity to positive infinity, or the book sometimes answers it as continuous at all x. All 3 of these are correct. When you're in My Math Lab, make sure that you're following the directions. If it wants the answer in interval notation, please choose the interval notation. Okay, so constant functions are continuous everywhere. Polynomial functions are continuous everywhere. Remember I said we had issues with rational functions. What's a rational function? A function that has that fractional bar. It's continuous at all x except for the places where the denominator equals 0. Why? Because the denominator can't equal 0. Division by 0 is undefined. So rational functions are not continuous everywhere. We'd have to figure out at what real numbers, right, at what real x, so is continuous for all x except for those, we should say here, real numbers where key of x is equal to 0. So let's look at number 4 and 5 real quick, because both of these are rational functions, and then we'll go for the last 2. So these both are rational functions. How do I know it's a rational function? Because of the fractional bar. So rational functions are continuous everywhere except for where the denominator is equal to 0. So how do I find out where it's discontinuous? Again, you set that denominator equal to 0 and you solve for x. So in example 4, 2x squared plus 1 is equal to 0. If I solve for x, I move 1 over, I divide by 2, and then I'm going to need to take the square root of both sides to solve. And I end up with x is equal to plus or minus I square roots of 1/2, which is not a real number. Since it's not a real number, there's nothing to exclude. Therefore, here we are continuous everywhere. Or remember, you can have it as interval notation, negative infinity to positive infinity, or sometimes the book is going to say continuous at all x. Again, you do not need to write all 3 answers. 1 is fine, but you're continuous everywhere because there is no place where the denominator is equal to 0, no real number where the denominator is equal to 0. Let's look at example 5. Example 5, same thing, it's rational. We set that denominator, in this case 2x minus 1 equal to 0, and we solve for x. Add 1 to both sides and we get 2x is equal to 1. Divide both sides by 2 and we get x is equal to 1/2. 1/2 is a real number. So how do we answer this question? So we are continuous everywhere except x equal 1/2. If we have to put this in interval notation, we would say negative infinity to 1/2 union 1/2 to positive infinity. Or it would just be x such that x doesn't equal 1/2. Continuous at all x except for x doesn't equal 1/2. Any of those is correct. All right, let's look at the other two that we skipped and figure out how to find continuity using theorem 1 for that, and then we'll continue on to example 6. So we know that constant functions are continuous everywhere. Polynomial functions are continuous everywhere. Rational functions are continuous at all x except for those where the denominator is equal to 0. The last two deal with radical functions, so things that have a radical. And what we know there is if n is an odd integer greater than 1, so 3, 5, 7, 9, etc., then it's continuous everywhere. So the cubed root of x is continuous everywhere. The fifth root of x is continuous everywhere. The seventh root of x is continuous everywhere, etc. So anytime you have cube roots, fifth roots, seventh roots, ninth roots, etc., those are continuous at all x. If you have an even root, if n is an even positive number, so you have the square root, the fourth root, the sixth root, the eighth root, etc., it's continuous wherever f of x is continuous and non-negative. So the way that we deal with these types of functions is we're going to set the expression under the radical greater than or equal to 0 and solve for x. We're going to set the expression under the radical greater than or equal to 0 and solve for x, because the only way that it can be non-negative if it's greater than or equal to 0. And if we have that inequality, then we will figure out everywhere that the function is continuous and non-negative. So let's look at number 6, which deals with this. So number 6 says f of x is equal to the square root of x plus 1. And what we need to do is we need to use that theorem to figure out where we're continuous. Well, this guy is a radical, right, because it's got a radical. And it's the square root. So my index n is equal to 2, and that's an even number, which means what I need to do in order to figure out where I'm continuous is set the expression under the radical, which is x plus 1, greater than or equal to 0 and solve for x. Well, this is just a linear inequality. I subtract 1 from both sides, and I get x is greater than or equal to negative 1. So we can say we're continuous at all x greater than or equal to negative 1. We can have the interval notation of bracket, negative 1 comma to infinity, or we could just have it as x such that x is greater than or equal to negative 1. All three of these are equivalent answers.